Hello, everyone. My name is Jaime Bowen Varela, and I'm a part-time PhD student here at UC3M. My supervisors are Rodrigo Castellanos and Francisco Barranco. Well, I'm going to talk a little bit about hardware in the loop for active flow control in aerodynamics, a really long name. So just to give you a little layout of the presentation, firstly, we're going to talk a little about the motivation and problem, so why active flow control needs hardware-aware validation. Then I'm going to talk a little bit of the state of the art, basically where we're in the simulation only, control only, and learning only validation, and where they fall short. Then talk a little bit about the research goals, so build a progressive path from benchmark dynamics to FPGA-oriented hardware in the loop. Then the methods and experiment, Landau, oscillator, LQR, baseline, residual RL, and delay and constraint sweep. Then we'll talk about results and discussions, some preliminary results that I could get on my part-time PhD done, and a little bit of the future achievements about the drone transition, hard deployment path, and academic output so far. So first, the motivation. Normally, aerospace engineers are more used to basically having some kind of simulation-first validation. We have our equations, we have our system, and we try to build those blocks in our computer. We have our clean models and our real timing, and we have a limited exposure and constraints for hardware. That's the issue, because normally aerospace systems run on embedded digital controllers. We have strict timing and antecedent budgets, and we have sensor, actuator, and implementation limits. So the goal of all this is to be able to connect aerodynamic control research with realistic hardware execution constraints. The traditional validation gaps start a little bit with the high fidelity CFD, which is expensive and slow for real-time iterations. Then we have also the wind tunnels, which are valuable but really hard to iterate on. And then most control ideas, as I said before, are validated mainly as algorithms. Now, also about the active flow control realities, non-linear, fast, and highly uncertain dynamics. It's extremely sensitive to actuation and sensing delays. And we can see a real performance gap between software and hardware models. So the missing piece is a validation path that tests controllers as complete real-time systems and in a loop, preserving realistic timing and hardware constraints. Talking a little bit about the state of the art, we have 4 different blocks. The first one is the classical control, which it's really strong and hardware-friendly, but it's designed around linearized or idealized models, which we know doesn't really work well with non-linear systems. Then we have some linear control, some kind of machine learning, which can compensate really well non-linear effects, but they are opaque and often need to be validated. This is really important when we talk about, for example, things that we want to fly on an airplane in the future. Secondly, we have CFD and wind tunnel. It's physical meaningful, but really expensive and slow for control iteration. And then we have our hardware in the loop validation, which is mature in embedded domains, but it's not really connected to active flow algorithm design at the beginning. So the missing piece, as I said before, is a validation path that tests controllers as complete real-time systems. So we have 3 main research questions while doing this thesis and all the stuff that I've been working on. And the first one is, can a small residual learning policy improve a strong LQR baseline or on a nonlinear benchmark? Just to give you an idea of what residual learning is, it's just a mix between an LQR and a small neural net, just to give a little bit more of context. The second question is, under which realistic constraints does it help? Delay, saturation, slew rate, noise, or model mismatch? This is mostly for the hardware part verification. And the last question that we have is, can the learned controller stay small enough for a fixed point FPGA-oriented implementation? It can be FPGA, it can be a microcontroller. If you have any questions about that, I can respond later. The approach is progressive validation path. We're going to go from a non-linear benchmark to go through a real FPGA, put it on a drone, and try to make it fly. But the primary goal is to be able to have a repeatable hill methodology before moving to higher fidelity aerodynamic and drone simulations. This is one of my methods, well, the first method. We started a little bit with the Landau oscillator. Just to give you an idea, this is kind of what it looks when you have some kind of phase plot trying to solve to make it control. Then we're going to use a strong classical baseline, which is the LQR, which is basically a fancy way to linearize a system and control it. And then we're going to have the small learn correction. It's going to be what's called residual RL, which in my case is a 41 parameter neural net that is capable of giving some nice results. Finally, we add some hardware-aware constraints with delay, saturation, slew rate, noise, mismatch, a little bit of everything, just to make sure that what we're doing on hardware it's well. And finally, we have the hill execution, right? This is going to be living on a real example, or even like a simulated example in which we have a computer and a FPGA working together just to try to get all these together. So the method, benchmark and controller. So here we have our lambda oscillator, which is basically our control nonlinear benchmark for active flow control. Something simple, but meaningful when it comes to aerodynamics. And secondly, we can see our resident control. I haven't really put the equations for the LQR, but just to give you an idea, we have something like this, and then we start adding our residual control. The residual control is basically a small neural net, really easy architecture. It can be coded in under 10 lines of Python. And basically, it combines both things. But we're always limited by the LQR output. So we make sure that we have an accommodated experiment. As said, a small residual neural, 381, and only 41 trilinear parameters. The goal is to test if a small residual policy can improve LQR under realistic hardware constraints. The training loop, we start with random initial conditions, differential closed loop rollout, add-on optimization for the neural net, and best policy retained per delay value, and we use this cost function. This is just the way to be able to use well how fast our cost function it's achieved. And then to evaluate it, we have a Monte Carlo simulation with a delay sweep of 2, 4, 10, 20 steps, saturation and slave consideration, and we have a process to measure noise. And we are using this evaluation function to basically see if that's the correct approach. The good thing about this setup is that it enables us to identify peak gains and stability boundaries under hardware constraints. So here we have some results. After doing some Monte Carlo, some experiments, and having the lambda oscillator combined with all this, I was able to get a 9.3% average improvement over a nominal LQR, which, I mean, it's good for a small neural net, but it shows that at least what I'm doing, it's kind of working. We have some other results too that we can see here, the mean sitting time and the mean control energy. Basically, they're telling us that, hey, this thing seems to work. We can continue the process to see if we can validate this through a real experimental scenario. So, said before, what the results are suggesting? Well, we have the LQR is already strong enough. It works really well, but the residual learning is helping all these parameters work better with non-linear behaviors. Then the 41 parameter correction is a credible candidate for a hardware-oriented implementation. But as said before, we have some remaining questions, right? Which constraints regimes produce robust improvement? Because it's not always like we are like messing too much maybe with the LQR plant, with the model, and maybe that's not a real thing. Secondly, how sensitive is the result to training and initialization? And what fixed point precision is enough for FPGA deployment? This is more like FPGAs normally don't work with float numbers. They work with fixed point because if not, you need to do some implementation on FPUs, which are like float processing units. But the results indicate that residual reinforcement learning effectively complements classical control in hardware constrained environments. Conclusions and future directions. Well, for now, I'm going to continue a little bit trying to improve all these benchmarks. But the idea right now is to go more into the robotics realm, in the sense of having some kind of simulation platform using Gazebo, ArduPilot, and possibly ROS as an operation simulation step before going through better, higher active flow control models. The good thing about going into ArduPilot, Gazebo, and all these things is like I don't need a really strong baseline for aerodynamics, and it's really fast to iterate on. And the idea is that maybe in the future I can run this on a drone. So that's it. Thank you very much. This has been my presentation, and if you have any questions, please let me know.